This is flip class video number 4 of Chemical Engineering Thermodynamics 2. The content is based on chapter 11.8 on the textbook written by Smith, Manus, and Abbott. And today we will talk about fugacity of a mixture, but the mixture is liquid. So if we look into what we have learned so far, we talk about species in real gas mixture, and during that time we calculate or define fugacity in the mixture of fugacity of species in the mixture according to this equation. This one was derived in video number 3. And then if we apply this equation to the ideal gas mixture, we just put the superscript Ig for the whole equation. You get this equation, and under special circumstance of ideal gas mixture, this fugacity of the species I would become partial pressure of that species I. You take these two equations and subtract the first equation by the second equation, you get this equation. And on the left-hand side, this is a deviation from ideal gas, or this is a real gas property subtracted by ideal gas property, which is the residue properties. And then on the right-hand side, this is the ratio of fugacity coefficient. All right. And then in video number 3, we derive this equation further to get this relationship that tells that the logarithm of fugacity coefficient is partial molar properties written as this equation. And the right-hand side can be evaluated using compressibility factor, which you can convert into a measurable variable using equation of state. In this equation, it was derived as though we consider the first equation to be state of what we are interested in. This is our system. And then this one would be what we call reference state. So these two equations subtracted with each other can be thought of as deviation from reference state from our system. Now, we are going to do the same thing, but in this time, we are going to change the status of our mixture from gas into liquid. So if we consider species I now in liquid mixture, we learned so far that we can use the same equation. This equation was derived based on gas mixture, but it is applicable for liquid mixture. So the equation remains the same. However, the reference state must be changed because we cannot use ideal gas as a reference for liquid mixture anymore. Instead, we have to choose new reference state. In this case, if we choose the reference state to be pure species I, same species, but in the pure state, at the same temperature as a system. Now, for pure species, the partial molar free energy would turn to be molar and give free energy only, and then fugacity here would turn to be fugacity of pure species. This equation was derived for pure species. Note that the gamma here, the integration constant, remains the same. It's a function of temperature only. So if I take this equation as my reference state equation, and repeat the same process, take the actual state subtracted by reference state, you get the difference here on the left-hand side, and on the right-hand side, you get fugacity ratio. This ratio is called activity of species I in the solution. And on the left-hand side, this difference is no longer the residue properties because this part is not ideal gas properties. This one is pure species properties, which may or may not be ideal gas. Actually, it's not ideal gas anymore because we are not normally consider this one for liquid, right? So this is no longer residual properties. So we cannot find this one by using equation of state anymore. Now from this one, we are going to pause our derivation for the moment and skip to another special circumstance called ideal solution. Ideal solution is a solution in which all the molecules interact in the same force. So if we have the mixture of substance A and substance B, interaction between molecules between A and B, and between A and B are considered to be the same. So all intermolecular forces are the same. This is in the sense similar to ideal gas mixture, because in ideal gas mixture, interaction between all kind of molecules are the same, but they are zero. So therefore, for ideal solution, we have to assume the same mixing rule as the ideal gas. This equation, all the equations here, were derived based on ideal gas mixture. First one is a ideal gas, pure ideal gas species, and then the last three here were derived based on ideal gas mixture. Now, in ideal solution, we have to define equation for partial molar Gibbs free energy in similar manner as ideal gas mixture, like so. On the left-hand side, this is partial molar Gibbs free energy of species I in the mixture. This mixture is ideal solution, so therefore we put superscript ID over here just to signify that this one is ideal solution. On the right-hand side, the former equation remains the same as what we derived for ideal gas mixture. The G here is molar Gibbs free energy of pure species, and then which is the same as here, except that this one is for ideal gas. This one is no longer ideal gas. On the second term is a logarithm of mole fraction. In gas, we use Y to represent mole fraction, but in liquid, we use X, but essentially the meanings are the same. Note that the free energy of pure species I in this case is supposed to be the same state as the solution, so essentially we are looking at the liquid properties at the moment. Now, once we get this equation, we have to repeat the process like what we did for ideal gas mixture, in the sense that once we get Gibbs free energy, we can find the properties, other properties from Gibbs free energy. The first one that we have to find is partial molar volume. And according to fundamental relation, we get partial derivative of Gibbs free energy with respect to pressure at constant temperature to be volume. And if you apply this equation for partial molar properties, you put bar here and there. Now, apply this equation to this part of the equation here by differentiating the whole equation with respect to pressure. You get the first term differentiate with respect to pressure, you get this term, and then the second term to be this term. Our differentiation would be done with respect to constant temperature and constant mole fraction. And on the right-hand side, the differentiation of this term would equal to partial molar volume, just like what we obtained from fundamental relation here. We put ID just to say that right now we look into ideal solution mixture. If we take a look at these two terms, the first term would become volume. The first term here, if you notice, the form here is very similar to this one, but it is written for pure species. So essentially, this one is the molar volume of pure species I. The second term, on the other hand, you see that the denominator here is RT, logarithm of X, when T and X are constant. So if you differentiate it with respect to pressure, nothing we do not have any pressure on top, so differentiation turns to be 0. So that means partial molar volume of ideal solution of species I in ideal solution is the same as the molar volume of species I as it is pure. Secondly, if we look into partial molar entropy, from fundamental relation, entropy can be derived from partial derivative of Gibbs free energy with respect to temperature at constant pressure. So if we apply for partial molar properties, put the bar on top here, we put the bar on top over there. And then take this equation, differentiate it with respect to temperature at constant pressure, you get this part. The first part here, same here, this is the same form as this one, just written for the pure species. So therefore, the blue box here is essentially a minus of entropy of species I as a pure species. On the other hand, the one on the red box here, if you take the derivative with respect to temperature, this temperature here would disappear and you get R logarithm of xi because xi is considered as constant. So that means we can get partial molar entropy of species I in ideal solution written as a function of entropy of pure species and the concentration. Lastly would be partial molar enthalpy, and it would be derived based on definition of Gibbs free energy, G equal to H minus Ts. So rearrange the equation, you get H equal to G plus Ts. You put bar for all terms, you put ID just to say that we are looking for the ideal solution at the moment. Then earlier we already defined partial molar Gibbs free energy of ideal solution as well as partial molar entropy of ideal solution like so. So just plug these two equations back in here. You get this part. And then we realize that E here is H minus Ts. So therefore Ts and Ts over there would cancel out. This term and that term are cancel as well. What we have would be enthalpy of pure species H. So in summary, we can calculate volume of the mixture by using summability relation. You take partial molar volume multiplied by concentration and sum everything up to get the mixture properties. And then we derived earlier that partial molar volume can be related to molar volume of pure species according to this relationship. So plug this to here, you get this part. Similarly, we get the relationship for enthalpy. We plug this using summability relation as well. We can get the enthalpy of the mixture, and we can repeat the process for entropy and Gibbs free energy. Now we are going to rearrange the equation a bit so that this part will be considered mixture properties or the properties of the system after you mix the pure species together. This is mixture properties. On the other hand, all of these parts are pure species properties before mixing. So if I rearrange the equation a bit, the mixing part, the mixture after mixing subtracted by before mixing is called the change in properties by mixing. For instance, this one is volume. This is the change in volume by mixing. For ideal solution, the change in volume by mixing becomes 0. That means if we have species A with volume of 50 milliliter mixed with species B with volume of 20 milliliter, then my net volume of the mixture will become 70, no change at all. Same thing applies for enthalpy. For enthalpy, this is called heat of mixing or the change in enthalpy according to the mixing. For ideal solution, the heat of mixing becomes 0. That means when you mix two species which would becomes ideal solution together, there will be no change in enthalpy, there is no change in heat. The process is not either endothermic or exothermic. Temperature will not change. But for entropy of mixing is not zero, it is negative, because after you mix two species together, the system becomes more chaotic. That's why the entropy becomes more negative. And free energy can be calculated in the same manner. You see that all the equations here is very similar to what we obtain for ideal gas mixture. So if we compare the equation for ideal solution in liquid phase to the equation derived for ideal gas mixture, you see similarity. Everything looks the same except the superscript change from Ig to Id, and the notation for mole fraction changing from Y to X. The rest are the same. Let's recall the equation that we calculate for a liquid mixture. This is actual state of the system. Earlier, we used reference state to be pure species, and then subtract these two equations to get this equation and activity on the right-hand side. Now, take the equation derived for ideal solution, like this equation. If I rearrange the equation a bit, at the same form, you see that they are very similar. So, if I apply this equation, you should notice that this equation was derived based on ideal solution assumption, but this equation was derived in general. So if I apply this equation for ideal solution, then my actual state will become ideal solution. I will get superscript ID over here. And then the left-hand side of this equation and that equation would be exactly the same. So therefore, I can see that these two parts on the right-hand side are supposed to be the same. And RT would cancel out, and I get the ratio inside the logarithm supposed to be equal to xi. If I make a rearrangement, I get this relationship. This relationship says that the fugacity in the mixture of ideal solution is equal to mole fraction multiplied by fugacity in pure state. This is called Lewis-Randall rule, which is a very important relationship that we are going to use later on. Lewis-Randall rules, if you divide the all equation here by xi times p. On the left-hand side, this ratio is basically fugacity coefficient. But on the right, xi here and xi there would cancel out. You get ratio between fugacity of pure species over pressure that is defined as fugacity coefficient of pure species. So you get relationship of the fugacity coefficient. The one on the left-hand side is in mixture. The one on the right is pure species. So essentially, Lewis-Randall rule statement is that fugacity coefficient of species I in ideal solution is equal to fugacity coefficient of the same species in pure state. Now, if we go back to what we derived earlier for liquid mixture. Now, in this equation, we use pure species I as the reference state. If I change the reference state from pure species to ideal solution so that we can do the same things as what we did for gas. Remember, in gas mixture, the reference state is ideal gas mixture. So in order to make things similar, the reference state is supposed to be changed to ideal solution. So if I take ideal solution as a reference state in this manner, then the reference state will be changed from from this equation written for pure species to this equation written for ideal solution. And then apply Lewis-Randall rules for fugacity in ideal solution can be written as xi times fi according to this relationship, which is called Lewis-Randall rules. Then take the actual state subtracted by reference state. And then the gamma on this part and that part would cancel out. On the right-hand side, we get RT logarithm of this ratio. On the left-hand side, this is not residual properties. This is the deviation from ideal ideal solution. This is called excess properties. The meaning is very similar to residual properties, but it is applicable for liquid phase. On the right-hand side, this is defined as gamma, called activity coefficient of species I in solution. So we can simplify the equation here to get excess properties, excess partial molar gift free energy as a function of activity coefficient of the same species. And then if you take the equation derived for ideal solution, this is equation for ideal solution, you plug this here, then you get the same equation, the similar equation on the left-hand side as what we derive when we choose pure species as reference state. But on the right-hand side, it will be a function of activity coefficient. This equation will be later used in many applications.